A multi-agent system can return the right answer and still fail along the way. Accuracy measures the final outcome, while crash logs expose explicit breakdowns. Neither alone reveals fragile trajectories, hidden policy violations, or silent degradation. I'm Mehrdad. Let's close that evaluation gap. Accuracy is necessary, but incomplete. It tells us whether the system reached the required outcome. Production evaluation must also inspect the trajectory, test repeatability across comparable runs, and measure the resource profile. A trajectory includes plans, handoffs, tool arguments, state changes, retries, and recovery. The evaluated object is not merely the confirmation message. It is the complete run that produced it. Follow the second booking from intake. The policy agent knows this itinerary needs manager approval before purchase. The search agent finds a valid flight and hotel, but the booking agent acts before approval arrives. Verification catches the violation, cancels both reservations, waits for approval, then books again. The employee receives the correct itinerary, so an answer-only test passes. Yet the system crossed an authorization boundary, created avoidable financial exposure, and depended on recovery to look successful. Cancellation proves that repair logic ran. It does not prove the premature purchase was harmless, or that the same repair will work next time. The correct result cannot erase that path. If this analysis is useful, like the video and subscribe for the rest of the multi-agent evaluation series. Nothing in that run had to crash. Every service returned a valid response, the final database state looked correct, and the user saw no error. Crash-oriented alerts can therefore remain green. The relevant evidence may still exist in traces, tool order, authorization state, cancellation, retries, and call count. A crash alert surfaces a hard failure. Trace inspection reveals whether a successful-looking run violated controls or consumed unnecessary recovery. That requires structured events and state transitions, not only free-form messages that cannot be compared reliably. Complete traces improve diagnosis over output-only inspection, although exact agent and step attribution can still be difficult. Green service health and healthy execution are different claims. I use 4 patterns to organize investigation. They are a teaching framework, not an empirical claim about how failures are distributed. Hard failure means an exception, wrong result, failed tool call, or invalid final state. Fragile success reaches an acceptable outcome through a policy-violating, redundant, brittle, or unplanned recovery path. Behavioral drift appears when equivalent requests increasingly use different agents, handoffs, dependency orders, retries, or output contracts. Silent degradation keeps task quality stable, while calls, latency, tool result volume, or model cost rise. Each pattern suggests a different first check: outcome assertions, trajectory rules, repeated run comparisons, or release-aware resource baselines. These patterns can overlap. Their purpose is to direct the next measurement, not to force every incident into one exclusive box. Fragile success matters because recovery can conceal a broken control. In the travel run, approval is meant to prevent an unauthorized purchase. Verification is meant to confirm compliance, not routinely reverse completed transactions. Once booking bypasses the gate, cancellation reduces harm but does not restore the original safety mechanism. It may leave fees, temporary charges, inventory changes, or audit obligations. If verification repeatedly becomes the repair agent, the architecture has shifted from prevention toward compensation without an explicit decision. Research on multi-agent traces finds failures across system design, coordination, and task verification, so blaming one bad agent is rarely enough. Other recent work shows that apparently successful behavior can coexist with degraded role adherence or information flow in the system studied. The operational question is whether required roles, dependencies, and prohibitions held before recovery became necessary. Now submit equivalent travel requests several times under controlled conditions. One run uses the expected policy: search, booking, and verification sequence. Another skips the policy agent, then asks verification to infer approval. A third repeats hotel search after a formatting mismatch and invokes a more expensive model. Hold the request family, policy version, and environment stable enough that the comparison means something. Different paths are not automatically defects. Several trajectories may satisfy the same invariance safely. The evaluation should compare required and prohibited actions, dependency order, retry behavior, handoffs, and distributions within a task family. The repeated trial lesson from TauBench is simple. One successful run demonstrates capability, while repeated success gives stronger evidence about reliability. Video 2 will turn these differences into behavioral consistency and loop signals. Compare the travel workflow across releases. The itinerary remains correct, but search calls rise from a stable baseline. Tool responses become larger. Routine policy checks route to a more expensive model, and end-to-end latency moves upward. That is silent degradation only when the movement persists outside a justified envelope for comparable tasks. More calls can be appropriate for a harder itinerary, and a higher cost can buy necessary quality or safety. Baselines therefore need task difficulty, release identity, and success status beside every resource measurement. Measure cost per successful task, median and tail latency, call count, model routing, retries, and tool response size by task family and release. HAL shows why performance and cost should be evaluated jointly, while trace review can expose shortcuts aggregate scores miss. Separate research also cautions that token counts alone may miss latency from tool pauses, cache behavior, and oversized responses. The next step is to classify what the evidence establishes. Functional evidence asks whether the output was wrong, the final state violated an invariant, or a required step failed. Behavioral evidence asks whether the system used a disallowed, suspicious, redundant, or brittle path. Statistical evidence asks whether latency, calls, retries, cost, or path structure drifted relative to comparable healthy runs. These are evidence families, not a severity ladder. A single behavioral event can be catastrophic, such as purchasing without authorization. A statistical signal can become highly consequential when it persists across releases. Functional evidence may be direct while the business impact remains minor. In the travel example, the final itinerary supports functional success. The premature purchase supplies behavioral evidence, and rising resource metrics supply statistical evidence. The three can corroborate one incident, but they should remain separately queryable for diagnosis. Keep those judgments separate so the label never decides urgency for you. Prioritize findings on 4 independent dimensions. Impact asks what harm occurred or could occur. Confidence asks how directly the condition was measured. Persistence distinguishes an isolated event from a recurring pattern. Reversibility asks whether the action or state can be safely undone. The unauthorized booking has potentially high impact, strong trace evidence, and imperfect reversibility, even if cancellation succeeds. One latency spike may have low persistence and no user harm. A sustained tail latency increase can become urgent when it breaks a service commitment. Those dimensions determine alerting, investigation depth, release blocking, and who must approve remediation. Triage the observed condition and its consequences, not the name of the evidence family. For each request family, build 5 evaluation layers. First, check the outcome and machine verifiable invariants, correct traveler, approved budget, valid dates, required fields, and a consistent final booking state. Second, inspect trajectory rules and risk detectors, approval before purchase, required verification, forbidden actions, dependency order, and compensating recovery. Third, run comparable requests repeatedly and examine success, handoff, retry, replan, format, and path distributions. Fourth, baseline calls, tool response size, model routing, cost per successful task, and median and tail latency across releases. Fifth, route ambiguous cases to trace review, a calibrated rubric-based judge or human adjudication when the consequence warrants it. Automatic trajectory evaluators can diagnose specific competencies, but they should be calibrated against humans rather than treated as ground truth. Run deterministic checks on every change, repeated trials on representative task families, and deeper review where uncertainty or impact is high. Store the input class, agent and model versions, messages, tool calls, state changes, final outcome, cost, and timing together. That record lets a team distinguish a bad answer, a broken control, unstable behavior, and an inefficient release without collapsing everything into one health score. The answer tells you whether the run ended in the right place. The trajectory tells you whether the system is becoming trustworthy, or merely becoming better at hiding how it got there. Start by preserving the full run and applying the 5 evaluation layers to one important request family. Then make the threshold specific to its policy, risk, and telemetry. If this video was useful, subscribe to Multi-Agent Academy and connect with me on LinkedIn. I'll keep publishing evidence-backed work on agentic systems. In video 2, we will turn behavioral consistency and loops into measurable signals across repeated runs, without treating every valid path difference as a failure. I'll see you in the next one.